record on this. Okay.
Okay, great. Yeah, so thanks for having me here at this seminar. And now, given the audience, I'm still sort of, sorry, so I will be talking about this result that's sort of the headline result here. So a particular result about the structure of the resource theory of non-locality, and also of the resource theory of contextuality, and also explain how these resource theories relate to each other. But given the audience, I'll sort of give a slightly more categorical take on this talk and show a bit more of what's happening under the hood, or how my thinking goes behind the scenes. Whereas usually when I've given this talk, it's been more towards a physicsy audience, where I then sort of try to hide some of those intricacies a bit under the rug. That said, if some of the physics or some of the category theory goes over your head, but you understand the other part, that's fine. Everyone has their interests and strengths and weaknesses. But also, if there is any parts that you feel like would be clarified by you asking a question, by all means stop me and ask ahead. I'd rather us get more out of the parts we do cover, rather than ensure that we must cover everything that's possibly on the slides. So now let me first set up the background thing. This is sort of for motivation. We're not really going to talk much about entanglement theory, but the starting point is that the following situation in entanglement theory, which was seen as very surprising and interesting when it was discovered in the late 90s. So there can be this situation where, so in entanglement theory, people usually, you think of some parties sharing quantum states. Usually you think about the bipartite setting, so you have two parties sharing quantum states between them. And then you take your free operations to be those that don't increase entanglement. And usually this is captured by saying, or operationalized by saying that you take operations, you allow the parties to do local operations on their quantum systems, and they can also use classical communication freely. And now there can be this situation where there's two quantum states that you cannot transform from one to the other using these free operations. But if someone, in the paper they talk about entanglement Scrooge, so someone comes and gives them this extra state to them, then suddenly they can do this transformation. And moreover, this extra state they were given doesn't get spent in the process, so it remains uncoupled from the system at the end of the protocol, so you can then return it to the entanglement Scrooge and be done. And now in this situation, you'd say that this is a catalyst because, well, it makes something possible, that some transformation possible that wasn't before, but it doesn't get spent in the process. And now this is something you could talk about at the level of any resource theory whatsoever, where you have some notion of what your resources are, and some notion of what does it mean to transform a resource to another in a free way or a resource non-increasing way. So for example, you could study, I don't know, probability distributions and what distributions you can transform to others purely deterministically, so without adding further randomness. And now in such a setting, you don't say that when something similar happens, you have a catalyst. So when there's no transformation between two resources, but if you have this extra resource D as well, then suddenly you can transform one copy of E to one copy of F. And moreover, this extra resource D does not get spent in the process. And now conversely, it could happen in some resource theory that this never happens. And we can write it in the following way. So I prefer to write ordinary arrows for a protocol or a transformation, and then this squiggly arrow to denote that there exists some such transformation. And now if there's never a catalyst, if there's no catalyst in the resource theory, then that amounts to saying that whenever you have a situation like this that looks like a catalyst, so you have a transformation that transforms E to F, and moreover, there's this one copy of D on the side that does not get spent in the process, then you actually could do this transformation from E to F without using this catalyst D. And now the sort of headline result is that this is exactly what happens in the resource theory of contextuality. So now our resources will be various kinds of correlations. The tensor product then denotes having sort of, if you think of this as some kind of like non-local boxes or something like this, as having these boxes independently side by side, so with no further correlations between them. And then we have some kind of resource theory of what does it mean to transform correlations to others in a way that doesn't increase contextuality. And now the result is that in such a resource theory, there are no catalysts. So whenever you have something that looks like a catalyst kind of situation, then you can do the transformation even without the alleged catalyst D. And now, I mean, there's a, sorry, I'll close the window so that the noises from the street don't bother us. Anyway, so people used to think for a long time that entanglement and non-locality are more or less the same resource. One is just a sort of entanglement at the level of probability distributions. But there actually is a known list of so-called anomalies of entanglement that show that these sort of behave differently as resources. And this result is yet another such difference between non-locality and entanglement, because, well, one allows for catalytic transformations and the other one does not. And now I'll give an overview of what's in the remainder of the talk. So I'll say some generalities about resource theories in general, some of which will be used later in the talk. Then I'll outline how our resource theory is built up. This is roughly something we've done in a prior work. But at the end of the day, what we're trying to capture is sort of a known operationally motivated resource theory that, I mean, physicists were already working with very happily before our work. So, I mean, depending on your viewpoint or your terminology, you might call it wirings and priority input classical communication, or you might talk about local operations and shared randomness, more or less the same thing. But now, I mean, the reason why we go through all this trouble of formalizing very carefully is that then it might help with some proof techniques, and in particular with this result here. And then I'll use the generalities on resource theories to explain how the resource theory of non-locality relates to that of contextuality. And roughly, it's sort of the end part that version of the resource theory of contextuality. And yeah, the main result is based on a paper by the same name. And here's a very short summary of the proof idea. So if you had this catalyst that would let you do this transformation once, well, because it doesn't get spent in the process, you could transform as many copies as you wish. And then if you think carefully through what happens for transforming large enough amount of copies, it will turn out that you only use the catalyst to provide you with some classical randomness, which is actually free in this resource theory, and hence you can do without it. So now, this is not really the way physicists usually think of resource theories, but it's certainly how I do. So for me, a resource theory, I'd roughly say that it's sort of a symmetric monoidal category, except the viewpoint is very different than usually in category theory, where people ask all these global questions about the category, like, you know, what sort of limits, co-limits you have, how it relates to other categories and stuff like this. And instead, in a resource theory, or if your objects really are resources, the main questions are of the form like, oh, if I have these two resources, is there a transformation between them? So is this particular home set empty or not? So in some sense, people don't often care about the symmetric monoidal category itself, but you could just sort of form its pre-order collapse. So quotient all the home sets to be singleton or empty, depending on whether they were empty or not before. But then concretely, you could then study questions like, oh yeah, you have some sort of channels with some amount of noise. Can you sort of use these and some encoding to get a noiseless or almost noiseless channel? And that's sort of something you do in information theory. Or then for entanglement, you have these LOCC protocols as your free transformations. But you could think of any abstract commutative monoid with some kind of pre-order on it as such a thing. And now this viewpoint that, okay, resource theories are kind of like symmetric monoidal categories is something that's espoused in this paper here by Kukia, Fritz, and Speckens. And there they give lots of constructions of resource theories from the following setup. So you have some ambient category of processes, and inside of it you have a subcategory that contains all objects, and then the morphisms in that subcategory, you interpret those as the free transformations. So you might think of the deterministic maps inside stochastic maps, or LOCC protocols inside all quantum channels, or something like this. And then from these, you can build resource theories in various ways. And one of the constructions they use is this resource theory of states, which is a good one to have in mind. So then you say that in this setup, you say, oh, a resource of some type is given by a state of that type, so a map out of the tensor unit. And then you say that a transformation between two states is a free transformation, so a transformation in the subcategory of free maps that transforms the first state to another one. And now this is an observation that they don't really, I mean, well, making the paper, well, they sort of hint at it, but don't really come out and say it. But my take is that actually most resource theories are somehow fit this kind of pattern. So they actually arise by doing something called a Grothendieck construction to some functor. So roughly you'd have some kind of category where you have your free processes, and then you have some functor that tells you for each object what are the resources of the type. And then you can build the Grothendieck construction or the category of elements of that functor. So let's recall briefly how that works. There's a whole big story of this construction, which I'm not going to recap here, but I'll say something briefly. So if you have any functor into set, you can then build sort of the corresponding category of elements. And the way it works is that your objects are pairs. Sorry, it shouldn't be complex numbers. It should be the same category C here. So your objects are pairs of an object of the original category and a resource R of that type. So I'm thinking of this F as giving you resources of type A. And then a map between two such pairs is given a map between the corresponding types that transforms the first resource to the second resource. And now it's a general fact that whenever your starting category C was a symmetric monoidal category, and then this functor F respected it to a reasonable extent, then this category of elements, so the resource theory you end up building is automatically symmetric monoidal. And I claim that this is actually the way most resource theories arise. So for example, the resource theory of sort of probability distributions or discrete probability distributions and sort of deterministic ways of transforming between them, you could build it as follows. So you start from you start from the category of stochastic maps. Inside of it, there's a subcategory of deterministic maps. And now if you think what's a map from the tensor unit with respect to the Cartesian product, which is not a categorical product anymore in stochastic maps, but it's still a fine monoidal structure, to some set A, well, that's basically just a discrete probability distribution on that set. And then if you work through what the category of elements is, you exactly get this thing where your object consists of a discrete probability distribution set, some set. And then a transformation between two such distributions consists of a deterministic function between the sets that transforms the first distribution to the second one. And now
I have
go ahead.
Yeah. Quick question. So in the previous slide, the one before this.
Yep.
Yeah, probably you may not be thinking of explaining in the slide, but I was just curious. So the last approach here, the commutative monoid approach of, I think it's due to Fritz.
Yeah.
How does it very roughly relate to the one that you're taking as the main approach, starting from a category C?
Well,
so how do you get?
That's a good question. I'd argue that, I mean, sort of a priori commutative monoid, you can think of that as a very boring kind of asymmetric monoidal category. So it's actually, I mean, your objects are then elements of the monoid, and it only has identity arrows and then all the properties of the all the isomorphisms required of a symmetric monodal category are actually hold as equalities on the nose. Sorry, I said false things there. So yeah, all the symmetric monodal isomorphisms are actual qualities in this case, but you do have the more arrows which are given by the preorder of the monoid. So any preordered commutative monoid is a particular kind of symmetric monodal category. And conversely, if you have a symmetric monodal category, if you then take the preordered collapse, so you just map all home sets into either the empty set or a singleton set, depending on whether they were empty or not, then you get a preordered commutative monoid. So as far as the sort of whether a given transformation is possible or not, the sort of both of these have the same kind of information. But then if you really want to not only know whether there exists a transformation, but want to think of the whole set of them and how they compose, then you might want to first start from the symmetric monodal category and then do the quotienting later, if at all.
Oh, okay, thank you.
So now another thing is, another trick you can do with this category of elements thing, which I haven't seen before, is kind of neat, which is the following. So if you have a symmetric monodal structure, I guess I'd want to take the copy of the free, the subcategory free things rather than everything, but let's just work with this case here. So in that case, the tensor product operation is itself, or I mean, well, now we're doing an n-ary tensor product. You need to bracket it somehow, but it doesn't really matter how. But it's going to be a symmetric monodal functor. And then you can again form the category of elements. And now what you get is the following. So what are your objects? Well, it consists of a sort of structure that's partitioned into a n-ary tensor product and of a resource state that's sort of on this tensor product. But note that the resource itself might be an entanglement resource. It doesn't have to be a tensor product state. And now a map between two such resources then consists of an n-tuple of free transformations that taken together transform the Sardine resource to the target one. And this gives us exactly this kind of n-party structure we'll need later. So concretely, I think of sort of a situation where you have n parties, and then together they try to agree on what free operation each of them together succeed in transforming this starting resource R to S. And now I'll move on to talking about contextuality, and this stuff is probably very familiar to many of you. So, but I'll recap it anyway. So the starting point is that we have some kind of systems where we can't measure everything at once. So you can only measure some things at once, and whenever you do that, you can. But when you try to fit it all together in the coherent picture, it somehow does not. It's globally inconsistent. And that's roughly speaking the probability distributions. So let's formalize this as we do it in the sort of sheaf theoretic or Abramsky-Brandenburger framework. So there you'd say that you have basically your starting point is this structure of a measurement scenario, which sort of are your resource types. And then for each resource type, you then say what the distributions are. So let's first go through what these measurement scenarios are. You have a finite set of measurements, and then you've specified which measurements are jointly compatible. And now I assume that if a set of measurements is jointly compatible, then any subset of it is jointly compatible as well. And moreover, I also assume that if you have a measurement in your set of measurements, then that should be compatible at least when done on its own. So any singleton measurement is compatible. But that means that the first parts of the measurement scenario have a nice combinatorial or geometric interpretation. So it's a simple abstract spatial complex. And then finally, for each measurement, you have some kind of outcome set. And for now, we assume that there are finite outcome sets so that we don't need to worry about any measure theory here. But in principle, you could generalize the framework and work with continuous variables as well. Talk about what are the relevant resources of that type. And those are these empirical models, which consist of having a joint distribution on the joint outcomes for each compatible measurement. And then throughout, I'll be assuming that we have this sort of generalized no signaling principle or no disturbance principle, which sort of says that whatever, if you're, I mean, if you're measuring some joint measurements, then the measurement outcomes for that measurement so in particular, if you're just measuring some things on its own and you get some outcomes, you'll get the same exact probability distribution that you'd get by than what you get by measuring a larger thing and then just ignoring the extra stuff. So marginalizing those away. And now here's a standard example of such a thing structure, but most of the important examples people care about do have it. So here we have two parties, Alice and Bob. Both of them have two measurements each. And then the jointly possible measurements are given by, well, either Alice measuring something just on her own, or similarly for Bob, or Alice choosing one measurement and Bob choosing one measurement. And then you could imagine them getting some data. So here's one famous example, the PR box, which is not possible in quantum mechanics, but we can get PR box and some classical randomness mixed in, which still gets us some kind of contextuality going on as well. So in this setting, basically Alice and Bob, for all of the three joint measurement choices, they get perfectly correlated outcomes with half-half probability. And then for one particular measurement choice, they get perfectly anti-correlated measurement outcomes with half-half chance. And now someone might then say, hey, I don't like this, that you can't measure everything at once. So maybe it's just an artifact of the theory, or maybe whatever it's coming from some experimental setup, and the experimental is saying, sorry, we can't measure everything at once. But maybe some better experimental setup will let you measure everything at once. And now, if that was possible, then you'd expect that there should be a joint probability distribution that explains all the marginal snapshots you've been seeing. But now, if there isn't such a thing, then your data is inherently shows that you can't measure everything at once. And then we say that the empirical model is contextual. So that's exactly the kind of situation where we have this locally consistent data, but you can't think of it as arising from a globally consistent picture that sort of we're just seeing partial snapshots of. So this limitation to just measuring some things and not everything altogether is inherent to the data we're seeing and not just an artifact of the theory or the experimental setup. Yeah, and now the important thing is that quantum mechanics predicts, and we've indeed seen stuff like this in the lab. So this is indeed something that seems to arise in nature. So let's now start talking about how to transform. So these are our resources. So let's now start talking about how to transform these resources to others. So I'll first start by talking about maps between the resource types. So if you had sort of two boxes, and S and T, and now we wanted to build the box T out of S. So you could imagine that they have a lab where they had the box T, but somehow it broke. And now they need to, the students want to, like running the lab, want to commit scientific fraud and sort of call this other lab where they have this box S and pretend that they still have access to this box T. And now for this to work out in principle, they have to have some kind of rule that tells them whenever they're being told to do some joint measurement in T, well, they should perform some corresponding measurement in S instead. Moreover, it should work so that whenever someone asks them a jointly compatible question from T, they never run into trouble. So they only end up asking compatible questions from S. Then they run S, get some answers, and then they have some rule that tells them how to interpret these outcomes as outcomes in T. And now let's write this formally, briefly. So concretely, it means that, or formally, it means we have two parts. We have sort of the pre-processing part, which is a function between simply shell complexes. So it's a function between the underlying sets, such that the image of any face is a face, so any compatible measurements, all compatible measurements get mapped to compatible measurements. And then we have these maps that let us process the outcomes. So for each measurement in T, we have a function that takes, we have a function that tells us how to interpret, let me say this more carefully. So if we take a measurement X, it's instead of measuring X, we're actually measuring pi of X. And now we have some function that tells us how to interpret outcomes of pi of X as outcomes of the original measurement X. And now we can then take this definition and then get a notion of what does it mean to transform correlations and not just these resource types. So then you'd say that it's a map between the resource types S and T that correctly transforms the first distribution to the other. So again, I draw the same picture as in the resource theory of states. So now, I mean, in this picture, I'm sort of ignoring the fact that there's sort of the pre-processing and post-processing part. I'm just thinking that we have this box D, and then we're interacting with it in a classical, in fact, deterministic way, and successfully transforming it into the box E. And this actually is the kind of category of elements construction before. So once we had the notion, we had these scenarios, and we had this notion of transformation, deterministic map between scenarios. Then you can write down a functor that sends any scenario to the set of all empirical models over it. And if you have a deterministic transformation between two scenarios, it will induce an action on how it maps empirical models of one scenario to empirical models of the other. And now when you take the category of elements of it, you get exactly this thing here at the top I've described. And an example of such a transformation would be that the PR box I had before, which was on a square, you could actually obtain that from a similar paradox on a triangle, basically by collapsing, say, one of the perfectly correlated edges into just a point. But now these are somewhat limited as transformations go. So there's two things you might want to add, at least, that are sort of operationally motivated and sort of done, are really classical behaviors, don't add contextuality. So you might say, hey, I don't want to map a measurement just to a single measurement of the other thing. You might want a measurement to be simulated by a whole set of measurements on the other thing, or you might want to be even more complicated. So you might want to say, hey, instead of measuring some fixed set of measurements on the other side, you might want to first measure something. Based on the outcomes, you might want to choose what to measure next. Based on those outcomes, we might want to choose what to measure next, and so forth. And eventually get some big list of measurement outcomes. And then finally, based on those, you choose what to output in the original box. And moreover, you should be able to freely use classical randomness. So you might flip coins and stuff like this during the simulation processes. So let's see how to add these to the theory. So we'll first add in adaptivity. And the way we do it is by sort of building a larger scenario from a starting scenario S. So we build a new scenario MP of S, where MP sort of stands for measurement protocols. And the idea is that the measurements of MP of S are these measurement protocols over S. And this isn't quite how we formalize it in the paper, but it's a snappy way of describing what they are, what these measurement protocols are. So a simple way of describing formally what a measurement protocol like this is by saying that, well, there's a empty measurement protocol, that's sort of your base case, nothing happens. Or you measure something in S, and then you have a function that tells you for each outcome what measurement protocol to proceed to next. And now these remaining measurement protocols have to be compatible with X. So they don't operate in S anymore, they operate in the link of X. So basically whatever is left of the scenario that is still compatible with X. And then what's an outcome for a measurement protocol? Well, eventually you'll have measured a bunch of things. Well, then you just return an outcome, an order list. So an outcome for each of the measurements you performed. And then you need to tell what's the compatibility structure on these. And in a nutshell, you'd say that a set of measurement protocols is jointly compatible if you could run them together or in parallel without ever ending up asking incompatible questions. So they should never, I mean, no matter what outcomes you're getting from the system, you'll never end up asking questions that are jointly incompatible. And then you can define adaptive transformations between scenarios by saying that, well, it's instead of a map from S to T, it's a map from MP of S to T. So concretely then that achieves exactly what we wanted. So now we're mapping measurements in T to these measurement protocols over S. And then we run S, we get some data, and then we have some outcome that tells us how to interpret the outcome of the whole measurement protocol as an outcome in T. And now if you want to add classical randomness, this is how we do it in the paper. Well, then we say that, okay, I mean, you don't only use sort of the first box, but you're also allowed to do a measurement protocol where you sometimes go and measure questions in this other box C with the requirement that this other box C should be non-contextual so that it only provides you classical randomness. That's one way of doing it, and it has certain benefits. So there's some generalizations that are easy to do, and we'll see maybe one later. But another way, if you really want to force everything into this category of elements point of view, is to instead say that, oh yeah, you have first had these deterministic maps, and then a stochastic but adaptive map is given by a convex mixture of these deterministic maps. So that's another way of doing it. So you could just take formal convex combinations of maps like this.
Martti,
and that would work. Yeah.
Just to be clear, so you're saying that in the paper, though, you don't do that second point, the alternative point of view is not established in the paper. Okay.
Yeah. And I mean, in terms of expressive power, so what transformations you get, they're exactly the same. So in that sense, it doesn't matter. They're not really the same category. So actually here also, if you really wanted to make a nice category out of this, you might want to form some kind of quotient here. So in some sense, if you replace C with the isomorphic copy, you might want to say, for example, that's basically the same map. And now you need to ask how much quotient you need to do to get the same category. And that's a question we haven't actually fully answered. But in terms of what resource transformations you get, so at the levels, the pre-order collapse, the difference doesn't matter. You get the same stuff.
Okay, very nice. Thank you.
Are you also doing MP of D tensor C or MP D tensor MP C? Or does it really matter?
That's a great question. No, I'm really doing MP of D tensor C. So that means that, I mean, so the difference is that, I mean, now a measurement protocol in over D times C can sort of, you can measure something in D, then go to C, and then based on these outcomes, go back to D and so forth. Whereas if you had MP of D tensor MP of C, then you sort of basically do a measurement protocol in one box, or you do a measurement protocol in the other box if you're only mapping measurements to single measurements. So we really want to be able to do a measurement protocol where you might go back and forth and use some of the randomness. Although when this box C is non-contextual, you could replace it basically by a single measurement that gives you the joint, samples from the joint probability distribution that you know exists. And you could assume that you always measure that or consume all the classical randomness at once. So in some sense, it sort of isn't this being able to go back and forth between the two boxes isn't too important here. But if you could then consider generalizations where you might say, oh, you're free to use any quantum box as your free resource C, then it could happen that this back and forth starts mattering at that point.
What do you exactly mean going back and forth between the boxes? Is that?
So I mean that if you think of what's a measurement protocol over D times C, then a general measurement protocol starts from one of the boxes, keeps doing some measurements and deciding what to measure next based on these outcomes. And it can then, based on these measurements, choose to go to the other box, and then based on those might come back. And in general, it can do arbitrary kinds of complicated behavior like this.
Okay. Because it's a disjoint union of the measurements.
Exactly. Yeah.
Okay.
Sorry. So I should have been precise and said what my tensor product of boxes is. So just to make sure everyone is on the same page. So my tensor product of scenarios is given by taking the disjoint union of the measurements, but at the level of the simplicial complexes, it's a join, which means that a measurement is compatible in S tensor T if its restriction is to S and to T is compatible. So basically you can do stuff in both, a joint measurement in both of the scenarios, and that will be a joint measurement in S times T. But as I said, in the particular case when C is classical, so non-contextual, you could always sort of replace a measurement protocol with one where you sort of consume all the classical randomness at once and then sort of use it to influence your decisions later as needed. Because the fact that you can't measure everything at once is not really a limitation for a classical box. It's only limited you when you're interacting with contextual ones. So now you can then define your simulations as follows. So now you say that a general simulation that allows for adaptivity and randomness from D to E is then a deterministic simulation of the form from D times C, from MP of D times C to E, where we require that this auxiliary resource C has to be non-contextual. And then this squiggly arrow, we can now give it a precise meaning by saying that there exists such a simulation for some C. And now, someone might worry, why do these maps compose? So, if you had one from D to E and then another one from E to F, you might then worry, you have one from MP of D times some resource to E, and then you have another one from MP of E times some other resource to F. Well, how do you compose them? And now this is something I sort of gloss over for a physics audience, but here I'm happy to say something. So the basic result that guarantees that this works is that this operation sending a scenario to MP of S is a comonad on the category of scenarios, and moreover it's comonoidal, which roughly means that it works nicely with the monoidal structure, and that implies that the kinds of definition on the previous slide composes nicely. So formally we move to the closely category of this comonad, and now if you don't know too well what monads or comonads are, in a nutshell, it's the short time would be that it's exactly kind of structure that guarantees that defining maps like this. So defining a new kind of map from S to T to be a map from MP of S to T. A comonad is exactly the kind of structure that lets you compose those kinds of maps nicely. And roughly, I'll say where the kind of structure that you have from a comonad comes from. So we have this co-multiplication thing. And now, again, the confusing part about the maps of scenarios is that at the level of measurements, we have maps going in the other way. So if you have a measurement protocol of measurement protocols, so a measurement here, So that means that it's something like, oh, first person perform this measurement protocol over S, based on the outcome, do that measurement protocol, based on the outcome of that measurement protocol, do that measurement protocol, and so forth. Well, you can always sort of flatten it, unroll it into a single measurement protocol where you first do everything that the first measurement protocol tells you to do. Then based on the outcome of everything you've seen so far, you then perform everything the second measurement protocol tells you to do, and so forth. And that's roughly how the co-multiplication works. Then we have a co-unit that lets us simulate the scenario S from MP of S. And that just works in the sort of obvious way. So you can think of any measurement of S as a very boring kind of measurement protocol that just measures a single thing, and then regardless of the outcome stops there. And then the comonoidal structure comes from maps like this. So we have sort of interaction between the tensor product and this MP structure. So if you have a measurement protocol over S, you can think of it as a measurement protocol over the disjoint union of S and T that just never does anything in T. And similarly for T. So all in all, this gives us a map from all the measurements of MP of S times MP of T to measurements of MP of S times T. And all these together satisfy some coherence laws that then makes all of this previous definition work. And now this is sort of really the resource theory that I think it works very nicely for contextuality. So first of all, I'd argue, it captures all the examples I know people have studied in the literature prior to us, where they write down transformations between correlations with some with some caveats though. So in the case where you study exact transformations between boxes, and you are allowed to use sort of a single copy of the starting box to transform to a single copy of the target box. So sometimes people also study sort of some relaxations of this, where you might then study questions of, oh yeah, imagine you have more and more copies of the PR box. Can you get closer and closer to the target correlation? And that's something that's not exactly captured by this framework, but you could imagine then building it on top of this if you really wanted to. And now that we've gone through all this trouble of making things precise, it does make some things easier. A lot of it at the end of the day boils down to very simple facts. So basically we have simplicial complex. A map of scenarios has an underlying simplicial map, and stuff like this, very, very basic things. But once it's all being written out, it's nice to have that handle that lets us prove results. This resource theory also interacts nicely with the contextual fraction. And this is something maybe would have been more interesting to go into more detail here, but you can show that in this resource theory, a correlation is contextual if and only if you can't simulate it from a trivial model. So basically the unique distribution on the empty scenario. And you can actually do versions of this if you change slightly the notion of simulation. So if instead of saying that you have this equality of distributions, you say you have an equality at the level of supports, or an inclusion at the level of supports, or something like this, then this kind of, is a correlation simulable from the trivial model or not? You can then by changing the category slightly, get this notion to capture logical contextuality as well, or strong contextuality as well. And now I can outline the proof of the headline result. And it's roughly what I said before, but now we actually know in a bit more detail what these symbols mean. But again, I don't want to go too deep into the weeds, so it's still a high-level proof sketch. But the first thing that helps make things simpler is that, well, formally, if you have a transformation from D times E to D times F means that we have some kind of adaptive transformation from D times E times some classical randomness C to D times F. But you can then show that you can just replace E with E times C. So E times this classical randomness, think of those as a single box. And now D is a catalyst then for that transformation. And now this transformation is purely deterministic. We've sort of incorporated the classical randomness just into one of the boxes. And that helps analysis somewhat. And then the other key fact is that if you can use D to make the transformation once, you can do it as many times as you wish. And now there's only finitely many ways of interacting with this catalyst D in a deterministic way. And now there's sort of a part where we think of what really is the simplicial complex structure on very large amount of copies of F. But what follows from this is that if you think of simulating very many copies of F, and one copy of F might have you interact with D in one way, another copy of F could make you interact with D in some other way, and so forth. All of these have to be compatible with each other because, by the definition of a simulation, we have a map of simplicial complexes and stuff like this. But that implies that all the possible ways we might ever end up interacting with this box D have to be jointly compatible. So we really need a part of D, or rather MP of D, that is only a jointly compatible subset of it. But that means that if you just restrict to that jointly compatible subset, well, that part where, well, everything is jointly measurable there, so then by definition, that's non-contextual. It's only giving you classical randomness. But now in this resource theory, you're always free to use classical randomness to help your resource transformations. So instead of using all of D, we can replace D with sort of only the part of D we use, which is only giving us classical randomness. And now we have an ordinary simulation going on from E to F. And we've gotten rid of this auxiliary resource D. And now I'll say briefly how the non-locality case then fits in. So at the level of resources, I'd say that non-locality is really the same phenomena as contextuality. So the lack of global probability distribution explaining the marginal distributions we're observing. The difference is that we're assuming that our scenarios have this n-partite structure. So you have like Alice has this part, Bob has this part, Charlie has this part, and so forth. And then they share some joint correlation. But otherwise, it's the same phenomenon. But there is an important difference at the level of transformations, which is that if you consider three parties, for example, trying to transform some shared boxes they have to some others, then when they interact with their system, they only should interact with their own part. So that means that Alice should only, when Alice is doing her part of the simulation, he should only, when someone asks a question from Alice, then Alice should only move to the boxes she is using to do the simulation and ask questions from those parts, and not ask questions from Bob's boxes or Charlie's boxes and so forth. But that means that they sort of each agree on what they do on their own part and how to, and then collectively this should succeed in transforming the starting resource D to the target resource E. But that's exactly the kind of construction I said earlier. So basically you take if you had a previous category of elements from some functor from scenarios to the category of sets, well, now you pre-compose this with the n-partite tensor product functor, and then take the category of elements, and that's exactly the resource theory you get. And now if you wanted them to share classical randomness, you could do the same kind of thing we do here. So they agree on each party doing their own thing, where they only query their own part of the box and their own part of the shared randomness state C they have. or you could allow them to take convex mixtures of joint behaviors, and it will give you the same expressive power. And now this is a neat way of capturing this idea of, okay, you have n parties, each does their own part, local operations on their part of the system, and then they share some randomness. And now if you analyze carefully the previous proof or a particular version of it, you will then see that, well, I mean, formally, if you had a simulation like this, well, then the proof will produce a simulation from E to F as well. But if you look carefully what kind of simulation gets produced, it will respect this n-particle structure. So Alice will still only be asking questions from her parts of the box E and her parts of the shared randomness. So the same proof will go through, and the result will hold in the resource theory of non-locality as well. And actually, the same proof works even slightly more generally. So we didn't really need that heavily the assumption that the auxiliary boxes, the shared randomness boxes, are classical. We need the following things. So you could try to generalize this notion of what does it mean to be a free transformation. And instead of saying shared randomness or shared classical randomness, you could say, oh, you're freely allowed to use shared randomness in some class X of correlations. So you could, for example, make all quantum realizable correlations free. And now the theorem works as long as this class X has the following things. So first of all, X should contain all non-contextual models. And the reason, and that's something we really need for this theorem to hold, because, I mean, the way the proof works is that we realized that, hey, we only need this claim catalyst D for classical randomness. And if that classical randomness is free, so in this class X, then it still works for the theorem. And the other thing we need is that this class of free random boxes that we're allowed to use, it should also be closed under tensor product. And the reason we need that is just for these simulations to compose nicely. And provided those hold, then the result still holds, whether or not, and both in the case for sort of X-assisted contextuality, or if you want to do this sort of n-particle version of it, the same result, same proof still holds up. And now this seems awfully general, but it sort of actually has some kind of concrete meaning to it. So even if we say, oh, we can freely use quantum correlations to do things, and then aliens showed up and gave us some black boxes that gave us a PR box, there's no smart way we can sort of use these PR boxes as a catalyst and not waste them in the process. If we really want to use these PR boxes to get some information processing done or coax communication complex or whatever, it will inherently involve us destroying the correlations there. We can't just use them to catalyze something we couldn't do before. And that's it. Thanks.
Thank you, Martti. I'll do the clap. No, that was very nice. Can I ask if anyone has any specific questions? 1 second, let's take a look.
I have one question. So the MP construction, is there a way to interpret it in a more geometric way, like in a more simplicial complex way? Like you said something about the tensor, it's like the join of the complexes.
Yeah.
So the MP construction, is there a way to see it in a more geometrically?
Yeah, that's a great question. I'll first say of a related construction that's sort of a bit weaker. So the way I motivated the MP construction was saying that, hey, maybe you don't want to map a measurement to a single measurement, but you might want to say that you map a measurement to a joint measurement in the other box. And this is something I roughly did in my sort of first paper trying to talk about these topics, where I talk about simplicial relations. And you could capture that by using another kind of comonad where that works as follows. So given a Actually, it works by, we sort of transform the direction of maps. So there's a monad on the category of simplicial complexes that does the following. So given a simplicial complex, you build a new simplicial complex whose vertices are the faces of the original complex. And a set of these new vertices is a face of this new complex if and only if the union of the corresponding faces was a face in the original one. So this will capture now this idea of, it won't have this adaptivity, but it will let us do this thing where you map a single measurement to a joint measurement of the other box. And that's still a nice resource theory. It's not quite as general. There are some transformations where you really need this adaptive behavior, but I think that has some kind of geometric interpretation. I'm not sure which one it fully is, but I think it's somehow related to these kind of subdivisions or something like this, or the phase complex or something like this that people do with simplicial complexes. For the MP construction, it's actually slightly more trickier, because I'd argue that it's not really just a construction on the simplicial complex. It's actually structure on the measurement scenario. So, I mean, the difference is that measurement scenario has also the additional data of outcome sets for each measurement. Roughly, I mean, what you need to do is, know the cardinality of the outcome sets. But I mean, basically what happens is that, you measure something, then you get some outcomes, and then depending on the outcomes, you proceed to do something else. But now how many options you might proceed to depends on how many possible outcomes you had. So the same simplicial complex, if you had only binary outcomes, or your outcomes had outcome sets were size 5, or they were different for each measurement, then MP of that scenario would be different each time. And that makes it a bit difficult to understand geometrically what's going on. But maybe there still is a nice geometric interpretation, I don't know. Perhaps the way to find that would be to just think of the binary outcome case, and then maybe see if you can make sense of that, and then start generalizing from there.
Okay, thank you. Yeah, any other questions? Yeah, Martti, I had maybe a sort of simple question. So like when I'm sort of thinking about constructing a resource theory, so what you had in mind is that I have these free resources, which are like the non-contextual box, which can be written down as sort of these empirical models that have this joint distribution. So that's kind of like a natural fit. Are there any other sort of like natural sort of resource theories where the free resources are something else? I don't know, maybe that's not a well-framed question, but
wait, so I guess, here you could do variants of this. So one thing is that you could, in some sense, if you just say, oh, you only allow deterministic boxes that don't really do anything for you, then you get this sort of a boring subtheory where your transformations are always deterministic. Or you could enlarge it by say, oh, you take quantum correlations as free, and then you can study what can you do with, like, I don't know, PR boxes or other super quantum boxes. And now all quantum boxes are basically free, so they will always be interconvertible. So that's in this setting. But now, of course, if you're in a very different kind of setup that sort of doesn't fit this pattern at all, then I'm not sure how well the question makes sense. But I guess there's, in general, people will have all kinds of different notions of what the free states are. That really depends heavily on the resource theory.
Okay. Yeah. I guess that was kind of what I was wondering. So thank you.
Yeah. So as an example, I think people study. Yeah. So there's a whole, big industry of quantum resource theories, which are roughly speaking sort of arise from taking some subcategory of CP-TP maps as your free maps. And then usually they have more structure. So then you assume that the set of free operations is convex. Well, it's actually convex here as well. But because everything is so closely related to quantum mechanics, there's quite a lot of analytical tools and entropies and what kind of stuff that lets you
could you repeat that Sorry,
quantum resource theory would be the keyword to look at what people do in way more physics end of things. And there people study questions like, I mean, there's resource theories of thermality or athermality or stuff like this, or coherence, or you might have a situation where you think of, I think there's even a resource theory of imaginarity. So I mean, basically, whether your quantum state, you can write it just using real numbers, or if you need to use complex numbers in, I mean, assuming some fixed basis, I guess, you can make a resource theory out of that. Or people have resource theories of channels. So instead of your quantum states being the free things, you take some kinds of restricted kind of channel to be free. And then you ask, oh, if you had a more powerful channel, but you can only do some kind of free stuff to it, can you transform it to some other channel? Yeah, so there's a big family of all kinds of stuff like this that people study in those kinds of frameworks.
Oh, excellent. Thank you. That was very good. I'm going to stop the recording and we can continue this discussion, offline, but just, I think that this is the natural breaking point for the recording at least. So I'll do that.